Hello class, we're back for part 3 of section 8.1, page 53, and here we're going to look for which values of R the what's known as geometric sequence R to the n converges. Okay, so this is actually called a geometric sequence. All right, and so what we're going to do is we're going to run through some common R values, and then I'm going to keep like a number line here, and I'm going to check off or put an X through whichever R values don't work. So let's pick some low-hanging fruit here. So let's start with R equals 0, right? And now we're going to start our sequences with n equals 0. So if you want, like, you can write, like, n is going to go from 0 to infinity, like that, right? Okay, so when R is 0, well, I get 0 to the 0, 0 to the first, 0 squared, and so on. And technically 0 to the 0 is undefined, but we usually define it to be 1. But then all the rest of these, 0 to any power, is going to be just 0. And so we have to ask ourselves, does this sequence converge? Are these values settling down as we go on farther down the list? And I think the answer is yes, right? They're all settling at 0. So I think what we're going to say is that we get a convergent sequence when R is equal to 0, and the limit is 0, right? So this is convergent. So I'm going to put a check mark right here at 0. Okay, let's pick some more low-hanging fruit. How about R equals 1? Well, we get 1 to the 0, 1 to the first, 1 to the second, 1 to the third, and so on. That's just, well, 1 to the 0 is 1, and then 1 to any other power is also 1. So this is just a list of all 1s. And so the limit as n goes to infinity of 1 to the n, well, you just get a list of 1s. Is this settling down somewhere? Yeah, it's settling down at 1. And this is convergent as well, right? Okay. Some more low-hanging fruit. How about R equals minus 1? Okay. So we get minus 1 to the 0, minus 1 to the 1, minus 1 to the 2, and so on. And so what we get is minus 1 to the 0 is 1, minus 1 to the first is minus 1, minus 1 squared is 1, minus 1 to the cube would be the next one, which is minus 1, and so on, right? And so you have to ask yourself, are these values settling down to one single point? And I think the answer is no, right? And in fact, we saw on the previous page, where is it? Right here, that minus 1 to the n, which is really what we're getting, is a divergent sequence, right? And so we're going to say that this is actually divergent. And so above minus 1, I'm going to put an x, right? That one's no good. All right, so let's look at the rest of the number line here. The first one I'm going to look at is this interval 0 to 1. So we're going to say 0 less than r less than 1. And now what I'm going to do is, like, really what we have here is r to the 0, r to the first, r squared, and so on. Any number to the 0 power is 1. R to the first is r squared, r cubed, and so on, right? That's not very helpful. It's not helping us see if numbers are settling down anywhere. So what we're going to do is instead look at a representative value. Like, what if, pick your favorite number between 0 and 1, about like 1/2. If you picked r to be 1/2, you would give 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so forth, right? I think those are starting to settle down near 0, right? Because you get just 1 on the top, but larger and larger numbers on the bottom. And so for numbers r strictly between 0 and 1, the limit is also 0, and that's convergent, right? And so in this whole region here, I get a check mark, right? Let's pick numbers bigger than 1. So r greater than 1, okay? And once again, it's the same deal. Like, you get 1 r squared, and so on and so forth. But now pick a representative out of this batch here, so way over here. How about like 2, right? You can get 1, 2, 4, 8, 16, 32, etc., etc. Those are not settling down anywhere. They're, in fact, blowing up to infinity. So I think here we're going to get a divergent for r greater than 1, right? And so this whole region, I'm going to put an x above it. Now let's do the same thing on the other side. So for -1 less than r less than 0, well, once again, I just get 1r, r squared, r cubed, so on and so forth. That's not helpful. So what I'm going to do is I'm actually going to use the star theorem above from the previous page that I highlighted. So go ahead and watch the previous video if you haven't to see that one. But let's look at what happens when I do the following. When I take the limit of the absolute value. Well, rules of absolute value say that this power can actually move out. So I get the limit as n goes to infinity, absolute value r to the n. And now look here. R is strictly between -1 and 0, so its absolute value is between 0 and 1, right? Well, when the value is between 0 and 1 and you raise it to the nth power, that limit goes to 0. So because absolute value r is now positive and between 0 and 1, this limit will be 0. But by star theorem, we conclude the limit as n goes to infinity of the sequence that I really want, which is this r to the n, also has to equal 0. And this is for -1 less than r less than 0. So in this range here, I also get a check mark. All right, and now finally, with r less than -1, well, once again, it's 1r, r squared, r cubed, etc. This is not helpful, so pick a representative value. How about something like -2? You can get 1, -2, 4, -8, +16 would be the next one, -32 would be the next one. Those are not only bouncing back and forth, but also getting bigger as they do it. So you get something that kind of looks like that, right? And that's certainly divergent, just by looking at the picture. And so in this region here, I also get an x over it. So now let's collect, and we'll put our answer here in this little box here. The sequence r to the n converges if, well, let's see, r can't be -1, but it can be like any number bigger than -1 all the way up to +1. If r is strictly bigger than -1, but less than or equal to 1. Okay, and the limit as n goes to infinity of r to the n equals 0. Well, if -1 is less than r less than 1, and limit equals 1 if r equals 1. Right? So just go back here and look at the actual limits that we got. They were always 0 if they existed, unless r was equal to 1. Okay, so coming down here, we're actually not going to do the monotonicity or the rest of this section. We're just going to do this last part here, and that'll be the end of this section, 8.1, just for the sake of brevity, since I want to get to series soon. So let's look at this sequence and let's try to determine if it converges or diverges. And if it converges, let's find its value. So notice this sequence an is 3 to the n plus 2 over 5 to the n. Well, we're going to use rules of exponents to simplify this. So this is 3 to the n times 3 squared over 5 to the n, right? 3 squared is 9. So this is 9 times 3 to the n over 5 to the n, which equals 9 times, and now these are both raised to the power n. So that's the same as 3/5 all to the n. Right? And so I guess my question then is, what is r? Is there a what's known as common ratio? Well, yes, I think r in this case is 3/5, right? It's the thing being raised to the n power. right? That's what a geometric sequence is. It's something being raised to the n power. And so now the limit, I'll say, so the limit as n goes to infinity of an is the limit n goes to infinity 9 times 3/5 all to the n. Well, the 9 doesn't really affect anything because this r is strictly between -1 and 1. It's going to go to 0 as n becomes large. And so this is like 9 times 0, right? Which is just 0. And so this is a convergent, so an converges. Okay, so that's the end of section 8.1. We're not going to bother with monotonicity or the page that follows. In the next section, we get into 8.2, which is series.